Alright, today we're going to introduce logarithm mean value inequality, which is similar or related to the AMGM inequality that we're familiar with. Of course, this is a follow-up video regarding some basic logarithm inequality we introduced last time. In that case, we try to compare log x with a linear, x minus 1, right? So we have some inequality in that give us the range of logarithm function. Today we're going to have another inequality which provides a tighter bound on that inequality, and from that inequality we're going to derive what is called the mean value inequality for a logarithm function. All right, so let's get started. As we recall, the inequality we got last time is this illustrated in this diagram here, where the straight line y equal x versus log 1 plus x, and versus the blue line, which is x over x plus 1. Of course, you can use change of variable. You can shift x by 1, and you can have a corresponding, inequality in different form. All right. So today we're going to look at three functions here, right? It's log and the two functions that we try to sandwich the value of log x. First, we make note that the domain of those functions, we assume x is positive. And we also notice that when x equal to 1, three functions are all equal to 0. So in other words, f1 equal g1 equal h1 and equal 0. So we want to compare the relative value of f and g and h. They have common value at one point. So one way of doing analysis is actually take a look at the derivative of f minus g and f minus h. What is the derivative of this function, right? So let's do that. Now, individual derivative is actually, the derivative is linear, right? So we can just try to find out what's the derivative of f, g, and h. That's very easy. So we have it here. Logarithm is just 1 over x. The g here is going to be this one and this one, right? So that's good. So, but we are interested in the comparative value of f and g. So let's evaluate what is f prime minus g prime here, right? So you plug in, by using 1 minus 2, yeah, that would equal to, common denominator is going to be 2x squared root of x, and here would be 1 minus 1 unit of time, the 2 square root of x, right? So 2 square root of x minus 1. You put elective here, and what you get here, it becomes x minus 2 square root of x plus 1. You notice that this is nothing but square root of a square, right? So you complete the square, you're going to get square root of x minus 1 square 2x square root of x. We are considering the domain of x positive, so the whole thing is elective. So in other words, the function f minus g is decreasing function here, right? Now, similarly, we're going to examine what is f minus h. All right, let's do that. So let's write here, this is the third equation here, 1 minus 3, 1 minus 3, all right? So f minus h, 1 minus 3, common denominator is going to be x times x plus 1 square. That would be x plus 1 square minus 4x. And if you expand it out, you find out that the top can be x1 minus square over x plus 1 square. X is positive, and this whole thing is always positive. So in order to f minus h is increasing. All right. So notice that strictly increasing, but then there's a common point at x equal to 1. So which means when x, greater than 1, yeah, so f would be greater. When smaller than 1, f would be smaller. So this behavior with h. G is just the reverse, the relationship, right? So from this analysis, what we get is that when x is smaller than 1 and bigger than 1, the f is sandwiched by, g and h, but in an opposite manner, right? In other words, the turning point would be x equal to 1, which is the turning point when they're equal to each other. When they are strictly greater or smaller than 1, we're going to have this inequality, or in the diagram, of course, this is kind of rewrite of plug-in, what is h and what is g, right? This is g, this is h. All right. So here in this graph, all right, so the turning point is x equal to 1 when x greater than 1, yeah. So the logarithm is sandwiched by two functions here, right? Yeah. So, and the other side, when x is smaller than 1, is just reverse, right? The green and the blue, the switch orders, right? So that's what do we get, all right? So this is the function g here. This is function h. This is the function h. This is the function g. And then, of course, this is a function h here, right? This is function g here, right? So that's what we got. The tighter bound from the previous inequality. Let's move on. Now, if I have two positive numbers, assuming a greater than b, the ratio would be greater than 1. We can plug in the inequality we just got here, right? And then let's see what is a over b, right? Let's just plug in, right? So 2a over b minus 1, a over b plus 1, smaller than a over b, smaller than a over b minus 1, square root of a over b. In this fraction, we multiply b on both sides, at both denominator and numerator. So what we get is 2a minus b, a plus b. This is nothing but log a minus log b. This is going to be a minus b, square root of a over b. Since a minus b is a positive number, we can divide a minus b on all the sides here. This become a minus b. This become 1. Since they're all positive, and the fraction, if we flip the fraction, you're going to change signs. So in other words, if you flip a minus b over log a minus log b, is going to be switch the order here. This becomes here square root of ab, and here 2a plus b over 2. That's going to be the main conclusion we have for the mean inequality. This is the am, this is the gm, this is the mean of the log, right? So we have this inequality here, right? So logarithm inequality here, we're saying that if here we're going to have this equation. Now you might wonder, we only assume a greater than b. What if a smaller than b? As a matter of fact, you can plug in the inequality here, and then you're going to derive the same identical inequality, which is the mean inequality here, right? So we're going to introduce some of the application of this in the next few videos, all right? So thank you again, and hope you enjoyed the video. Please like, share, and subscribe. Thank you.